Welcome to lecture number 32 of the course on nonlinear structural analysis, theory and applications. So, let us recall what we discussed in the previous lecture. In the previous lecture, we learned, or rather we refreshed our memory to calculate the principal stresses and the principal planes by solving the eigenvalue problem. Then I have introduced you to indicial notation. I am not sure whether you have done indicial notation or not. If you are a undergraduate student, you may not have done it. Okay. So, for graduate students, I am sure in mechanics course you have done it. Okay. Then we have talked about deviatoric stress tensor and the hydrostatic stress tensor, that any given state of stress can be decomposed into deviatoric plus hydrostatic. And then we talked about octahedral shear and normal stresses, and I have also discussed about the Hay-Westergaard stress space. Okay. So, in this lecture what we will do, we will briefly review the concept of strain and then talk about the generalized Hooke's law, that is relating the stresses with strain for linearly elastic isotropic materials. Okay. Once that is done, we will be in a position to study what happens when a body under general state of stress starts to yield, or on what condition we can determine that the body will yield or the material will yield or not. Okay. So, let us get started with strain at a point. As you know, whenever you take any body, okay, which is subjected to some sort of forces, strain at a point from one point to the other point will vary, right. This is easy to understand. Okay. So, let us first take a very simple case of uniaxial problem. Okay. So, here I have a member, right, where I am taking a small element AB, which is basically a straight line, okay, length of which is delta x, and I am setting delta x tending to 0. So, I am looking at strain at point A, right. So, AB is the length before deformation. After deformation, let us say point A has moved to A prime and B has moved to B prime. So, the displacement of point A is u, okay. Displacement of point B is u plus delta u, okay. And then this elongation of the bar is delta, okay. This is subjected to force P. Then we define the normal strain at point A is equal to limit delta x tends to 0, A prime B prime, that means the final length of this infinitesimally small segment minus its original length A B divided by its original length. That is how we define the normal strain epsilon x in the x direction. Now, what is A prime B prime? Well, A prime B prime is delta x plus u plus delta u minus u, that is what I have done, delta x plus u plus delta u minus u, and A B is equal to delta x divided by delta x. Now, you take the limit delta x tending to 0. So, what you get? This will cancel, then you have this will cancel. So, you have delta u divided by delta x tending to 0. So, basically this is du dx, as simple as that. If the deformation is distributed uniformly, then we can say that epsilon 0 is L, this is the final length minus the initial length divided by the initial length, okay, which is delta by L 0, delta is the deformation, right. If the deformation is not uniformly distributed or non-uniform, then this kind of gives you an average strain. Okay. So, this is simple uniaxial case. So, now let us talk about a body which is shown here, which is strained in two orthogonal direction x and y. Okay. At point O, which is at x y, the displacement is function of x y u x y in the x direction, and the displacement in the vertical direction or the y direction is v, again as a function of x y, right. Now, if I consider two small line segment which are perpendicular to each other at point O and show them here. So, OC is one line in the x direction and OE is the other line in the y direction, and they are mutually perpendicular, right. Now, after deformation, what happens? Point O goes to O prime, C goes to C prime, and the displacement of O in the x direction is u, in the y direction is v, right. Displacement of point C in the x direction is u plus change in u with respect to x. So, that is del u del x multiplied by the length of the line segment OC, that is delta x. So, this is the displacement of C in the x direction. Okay. Similarly, for y direction, point O has moved by an amount v and E has moved to E prime by an amount v plus change in v with respect to y, del v del y times its length delta y. Okay. So, now we define the normal strain in the x direction, which is epsilon x is in the limit delta x tending to 0, that means this line segment length is tending to 0, O prime C prime, that is this length minus this length divided by this length. Okay. So, what is that? So, if I write limit delta x tending to 0, O prime C prime is basically my delta x plus u plus del u del x times delta x minus u. This is my O prime C prime. And what is OC? Well, OC is delta x divided by OC, that is delta x. Okay. So, now this and this will cancel, this and this will cancel. So, after I take the limit, this basically becomes del u del x. Okay. Similarly, in the y direction, what you get epsilon y, the normal strain in the y direction is del v del y. Okay. Now, let us consider a body under plane strain. Okay. So, at the same point, let us say at the same point O, now I have considered these two line segment OC and OE as before, which are infinitesimally small. Now, this line segment can stretch, elongate and also rotate. That means, the angle which was 90 degree between them can change, which is now a different angle, right. So, O has gone to O prime, C has gone to C prime. Okay. As we have seen already, the epsilon x, okay, does not change, it is going to be del u del x, right. From here it might appear a bit tricky, but you can actually do a detailed derivation and show that epsilon x is going to be del u del x for small strains, when the partial derivative of the displacements are much smaller compared to unity, then this can be easily derived. Okay. Or simply O prime C prime minus OC divided by OC is del u del x. Okay. Similarly, the normal strain in the other direction is the same as before. Now, what about the shear strain? So, the shear strain, which is called gamma xy, okay, is basically what is this angle? This angle? This angle, as you can see, it was like this, right, and it has distorted, okay, because of shear, right. So, the distortion is basically this angle and here it is this angle. Okay. How much is this angle? Is nothing but the slope. So, if the displacement variable in the y direction is v, so change in v with respect to x is del v del x, right. So, this angle is simply del v del x, right. Similarly, this is del u del y. Okay. So, the total change in angle is basically this plus that, which is my shear strain. You can always do a more rigorous derivation, end up getting the same expression. In the interest of time, I am not getting into those derivation. Okay. So, just to remind you, the assumption is we are talking about strains that are small, much small compared to unity. Okay. So, for a general 3D problem, we now have three displacement components u, v and w. Okay. and all of them are function of x, y and z, and these are the displacements along x, y and z direction of point O. So, my normal strain becomes del u del x in the x direction, del v del y in the y direction, del w del z in the z direction. Just like for stresses, we used to subscript sigma xx, sigma yy, sigma zz, sigma xy and so on. For strain also we can say, instead of epsilon x, we can say epsilon xx, instead of epsilon y, we can say epsilon yy, and z epsilon zz. Okay. And the shear strain for a general 3D problem, gamma xy, okay, is equal to del v del x plus del u del y, which we have already derived for this 2D, gamma xy or equal to gamma yx del v del x plus del u del y, summation of these two angles. Okay. So, for a 3D problem, you will have 3 shear strands, right, gamma yx, zy and xz, which are equal as shown here. Okay. Now, how many equations are there? 1, 2, 3, 4, 5 and 6, right. So, this can be written in a very compact form using indicial notation. So, I can write epsilon ij, which is now used to denote normal as well as shear strain, okay, is equal to 1 by 2 del ui del xj plus del uj del xi. Okay. Also, this can be even written in a more compact form, where a comma is introduced to indicate this differentiation. So, ui comma j means del ui del xj, uj comma I means del uj del xi. Okay. So, if I just determine one of the components, so let us say I am interested in epsilon 1 1. So, this is 1 by 2 del u 1 del x 1 plus del u 1 del x 1, right. So, that means this is what, del u 1 del x 1, which is basically del u del x, right. Now, for the shear strain, what happens, let us take a look. So, epsilon let us say 1 2, okay. So, 1 by 2. So, my I is 1 and j is 2. So, del u 1 del x 2 plus del u 2 del x 1, okay, which I can write 1 by 2 del u del y plus del v del x, right. But what is the shear strain? Gamma xy is this quantity, right. If I say this is epsilon xy, right. So, you can see epsilon xy is half of gamma xy. Okay. So, I can also write this 9 components in a matrix form, and this is also a second order tensor, right. So, epsilon xx, xy, xz, yx, yy, yz, zx, zy, zz, and in terms of gamma, as you can see, these are all 1 by 2. Okay. So, this epsilon xy, yz and zx are called tensorial shear strands, whereas this gamma xy, gamma yz, gamma zx are called engineering shear strands. Okay. And the two are related. Just to remind you again, epsilon xy is equal to 1 by 2 gamma xy, yz is 1 by 2 gamma yz and so on. Okay. So, now let us talk about the generalized Hooke's law for isotropic materials. Okay. I am still talking about linearly elastic isotropic material. So, in a solid mechanics, a typical problem involves this. So, you have 3 displacement components which are unknown, u, v and w. Okay. You have 6 unique stress components which are unknown. Okay. We have 9 stress components and 6 of them are only unique. So, 6 stress components which are unknown. Then you have got 6 strain components, as you have just now seen, right. So, we have total of 15 unknowns. So, to be able to solve a theory of elasticity problem or a solid mechanics problem, okay, we need 15 equations. How do I get the 15 equations? So, there are 3 equilibrium equations which I have not discussed. Okay. You can go back to your solid mechanics book or the book by Crandall and Dull, okay, or Popov, and look at the equilibrium equations, okay, which relates the stresses with the external force. I will talk about this figure. And then we have got 6 strain displacement relation, which I have just now derived 1, 2, 3, 4, 5 and 6, right. So, 3 equilibrium equations, 6 strain displacement relationship. We cannot solve a theory of elasticity problem, right. So, we need additional equations because 15 unknowns and this is giving you 9 equations. So, we need 6 more equations and those 6 equations are called constitutive equations. That means, relation between stress and strains. So, in general, let us say you have a body which is subjected to some forces, okay. These are like some fraction forces, this is some displacement boundary condition, okay. F is the force and sigma ij is the stress tensor, epsilon ij is the strain tensor and ui is the displacement, v is indicating the volume, right. Just a schematic representation of a general problem in theory of elasticity. So, what are the variables? This and this, okay. And how they are related? Of course, the external force is also there. So, displacement and strains are related by the compatibility of the strain displacement relationship, right. Then strain and stresses are related by the constitutive relationship. Those 6 equations that we will see in just a little bit are called the generalized Hooke's law or constitutive laws, okay. And then stresses and external forces are related by equilibrium equation, which I have not discussed, right. So, this is how they are related. You have got 15 unknowns and you have got 15 equations to solve, okay. So, with that introduction, let us get into stress strain relationship. So, let us say for uniaxial case, you have one element which is subjected to sigma x only, right. We know the stress and strains are proportional and the modulus is Young's modulus, which is pictorially shown here. And this figure is taken from the book Plasticity for Engineers by Chen and Han, and the previous figure was also taken from the same book by Chen and Han, okay. So, this is schematically shown, E is equal to sigma x divided by epsilon x is the Young's modulus. So, this was a simple tension test. If you do a simple shear test, an element subjected to tau x y, okay. So, then the shear strain and shear stress are proportional and the modulus is called the shear modulus, which is the slope here, okay. If you do a hydrostatic compression test, an element subjected to pressure P from all direction, right, then what you get? You get the bulk modulus, which is defined as with a negative sign the hydrostatic pressure divided by the change in volume del V by V, and this is called the bulk modulus. It can be easily shown that del V by V is equal to summation of the normal strain epsilon x plus epsilon y plus epsilon z, okay. And this is showing a general 3D state of stress, right. And I am sure all of you have seen the relationship between E, G and nu, that, and this can also be derived. I will not be doing that. So, G is equal to E by 2 into 1 plus nu, and the relationship between E, the bulk modulus, and nu is K is equal to E divided by 3 into 1 minus 2 nu, okay. So, with that, now we are ready in a position to determine the 6 basic relationship between stresses and strains for homogeneous isotropic linearly elastic material. Homogeneous means same properties everywhere, and isotropic means the properties are same in all directions, okay. So, how do I derive that? So, let us say I have an element, okay, this is as shown here, and I am applying sigma x only, right. So, if I apply sigma x only, I will be getting strain in the x direction, which is sigma x divided by E, as simple as that. Then, because of Poisson's effect, there will be lateral strain in the y direction as well as in the z direction. So, y direction strain epsilon, I am calling it with a prime for a reason, okay. Epsilon y prime is minus nu into epsilon x prime. Now, epsilon x prime is sigma x by E. So, minus nu into sigma x by E. Similarly, epsilon z prime is minus nu into epsilon x prime. So, minus nu into sigma x by E, as simple as that. Similarly, if I apply sigma y, I am applying one at a time. Sigma x I have applied, okay, in this direction, Now, I will be applying sigma y, okay, in the y direction. So, if I do that, then my normal strain in the y direction, which I am denoting by epsilon y double prime, is sigma y by E, as simple as that. Lateral strains are epsilon x double prime, epsilon z double prime, which is this is equal to minus nu into epsilon y double prime, which is minus nu into sigma y by E, and similarly this one. Okay. Finally, if I apply sigma z, then I am using now triple prime, epsilon z triple prime is sigma z by E, okay, and these are the strain in the lateral direction, right. Now, if I apply all three of them, I apply sigma x, sigma y, and sigma z. Okay. So, what is my strain in the x direction? That is going to be epsilon x prime plus epsilon x double prime plus epsilon x triple prime. So, this plus that is going to be my epsilon x. So, superposing this strain epsilon x is equal to what I stated, that is 1 by E sigma x minus nu sigma y plus sigma z. That means, just adding this plus this plus this. Okay. Similarly, epsilon y is going to be the addition of the strain in the y direction for the three cases, that gives you this equation, and epsilon z gives you this equation, right. Shear stress is proportional to shear strain, as we have seen earlier, right. So, gamma xy is equal to tau xy by g, gamma yz is equal to tau yz by g, and gamma zx is equal to tau zx by g, where g is called the shear modulus. So, how many equations we have got? 1, 2, 3, 4, 5 and 6. So, these are the 6 equations we are looking for. Now, we have 15 unknowns and 15 equations. Okay. We will not be solving in this course, but you get the idea. Okay. If I use indicial notation, so this is the advantage of indicial notation, all this 1, 2, 3, 4, 5, 6, these 6 equations I can write in only one equation. Epsilon ij is equal to 1 plus nu by E sigma ij minus nu by E sigma kk delta ij. Okay. Now, how do I get the equations that you have seen before? So, let us see if I want to write epsilon 1 is what 1 plus nu by E, okay. This is sigma 1 minus nu by E. Now, sigma kk, this is repeated index. So, I will have to sum it over, right. So, I will have to do sigma 1 plus sigma 2 plus sigma 3 and this is delta 1. So, what do I get? So, I get from here sigma 1 by E, okay. This guy will cancel with that, okay. And then what I get? Minus nu by E sigma 2 plus sigma 3 and this is what we have already written earlier, sigma 1 minus nu into sigma 2 plus sigma 3. Okay. So, earlier we were using xyz, right. Okay. So, this is sigma xx minus nu into sigma yy plus sigma z or sigma xyz. Okay. Now, if you want to do the shear strain, then what happens? Epsilon 1 2 is equal to, so I is 1, j is 2, 1 plus nu divided by E sigma 1 2 minus nu by E. I will keep this sigma kk as it is, here I will write delta 1 2. What is delta 1 2? 0. Okay. So, that means this is equal to 1 plus nu by E sigma 1 2. So, I will simply go back to xy and simply say epsilon xy is 1 plus nu by E into tau xy. Okay. So, what is this? Let me go back to the relation between E and G. So, G is equal to E by 2 into 1 plus nu, right. So, from here I can write 1 plus nu by E tau xy by 2 G. Okay. So, that means gamma xy by 2, and this is what we have stated earlier, that the tensorial shear strain is half of the engineering shear strain. Okay. What if I write all the stress and strain components into vectors. So, let us say all the stress components I write in a vector of sigma with a subscript 6 to remind us I am writing only the 6 components. Okay? And similarly, epsilon 6 where I am writing all the strain components. Sigma 6 transpose because I am writing horizontally, sigma xx, yy, zz, tau xy, tau yz and tau zx. Okay? Epsilon 6 transpose is epsilon xx, yy, zz, gamma xy, gamma yz and gamma zx, right. Then I can write all the strains can be expressed a matrix times the stress vector, okay, which is this quantity, and this is called elastic compliance matrix, which has a size 6 cross 6. And if I invert it, then I can write sigma 6 is equal to C into epsilon 6, where C is called the elastic constitutive matrix, which has a size of 6 cross 6. So, now I will give you the form. So, this is my epsilon strain vector and this is my stress vector. So, what is this? This is the elastic compliance matrix, and in indicial notation you can write epsilon ij is equal to dijkl. So, there are 4 free indices, right, and this is a 4th order tensor. So, therefore, it has 81 components, but here you do not see 81 components, right, because I have written only the unique stress and strain components. Okay. Otherwise, there will be repetition. Okay. Alternatively, the stresses can be written in terms of strains, okay, where this matrix is called the elastic constitutive matrix. Okay. Using indicial notation, we write sigma ij is equal to C ij kl into epsilon kl, where this is a 4th order tensor. So, it has got 81 components, but you do not see it here because of the reason we discussed earlier, that we are working with only 6 unique stress components. Okay. So, theCijkl can also be written if I replace nu and E by K and G, bulk modulus and shear modulus, then this is the elastic constitutive matrix, okay, which will change when you go for a nonlinear problem. Okay. So, for the case of plane stress, what happens? Plane stress means, let us say a body in plane stress in the xy plane. So, that means the stresses in the z direction are all 0. So, sigma z is 0, tau yz is 0, tau zx is 0. Tau yz 0 means tau zy is also 0, tau xz is also 0. Okay. So, then this equation that I have shown earlier simplifies to this. Go ahead and try to derive this equation, okay, and you can also determine the strains in terms of stresses, which simplifies to this. Now, what happens to the normal strain in the z direction, epsilon z, is it 0? The answer is no, epsilon z is not equal to 0. But what about gamma yz and gamma zx? They are 0 because gamma yz and tau yz are related with the shear modulus and tau yz is 0. So, this is 0 and similarly that is 0, but epsilon z is not equal to 0. So, how do you determine epsilon z? Well, you can go back to this equation that we have derived earlier. So, in this equation, what you do? You substitute sigma z is equal to 0, then epsilon z is 1 by E minus nu into sigma x plus sigma y. Okay. That is what I have, and you can also write it in terms of the normal strain epsilon x and epsilon y. Okay. For the case of plane strain means you have a body which is, let us say, deformed only in xy plane. So, then we are calling the body is in plane strain in the xy plane. So, epsilon z, there is no strain in the perpendicular z direction, epsilon z is 0, gamma yz, gamma zx are 0. Okay. Then the equation simplifies like this. What about the normal stress in the z direction? Is it 0? The answer is no, it is non-zero. Okay. Again, going back to the previous equation, you can easily derive that sigma z is equal to nu into sigma x plus sigma y. Okay. Let us summarize what we have done in this lecture. So, in this lecture, we have briefly reviewed the concept of strain at a point, which is a second order tensor, right. Then we have discussed a typical solid mechanics or theory of elasticity problems, which involves 15 unknowns and 15 equations. Okay. We have not looked at all the 15 equations, particularly we have not looked at the equilibrium equations, okay, but we have looked at the strain displacement relationship and the constitutive relationship of the generalized Hooke's law. Okay. So, in the next lecture we will focus on what happens if a material or a body under general state of stress yields. Okay. How do we know that it is going to yield? What are the theories? Okay. So, that will be the discussion for the next lecture. Okay. So, this is the reference that I have used in this lecture. With that, thank you and see you in the next lecture.